Now we're going to move on to solve an actual reservoir simulation problem by hand using our knowledge of the central differences and the backward differences. So we're going to look for the 2p dx squared. So second order derivative of pressure with respect to space. And then we'll look for the first order derivative of pressure with respect to time. So those are the two things we're going to find numerically using those differences we talked about. So this is the problem we're going to model. Delta x is 200 feet, and it's the same everywhere, right? So this is all 200 feet. And the pressures are given at the face, at the interface between the matrix cells. So this is the face of the cell. So the pressures are given at the faces. P6 is going to be your flowing bottom hole pressure. So that's the boundary condition here. Remember, you need initial and boundary conditions. And the boundary condition here is a no flow boundary. So flux or flow rate across that face is 0. And you will see the way we will model that boundary condition. And these are some pressures just given here, right, at those interfaces. Good. The question is, what is P3, right? What is this derivative at, I can put a straight line here, right, at P3. That's what we're looking for. So again, that problem is similar to this, the 1D single phase problem, where we inject at one cell and produce at one cell. Whatever we do to solve the problem I just showed on the previous slide applies to this real 1D simulation problem. Now, I'm summarizing the equation we're trying to solve. This is what the equation looks like in 3D. Notice this, which doesn't show up in the other terms. Why? If it's a completely, if the grids are aligned with the X, Y, and Z directions, there will be no contribution to gravity in the X and Y terms, right? But in the vertical direction, gravity contributes. And that's why you see rho G showing up here. And the other terms are asked before. We are assuming all the non-linearity, so we are not assuming K, mean, rho, and phi are constant with respect to space or time. And this is precisely the equation we use in all of our reservoir simulation. And it is for a single phase flow. But if we simplify that equation further, and we only focus on 1D in the X direction, and we assume the fluid compressibility is small and constant, these three terms are constant like we derived before, you have this, right? We already derived this previously. For simplicity in notation, we can assume all of these terms are referred to as D, which is 1 over eta, and that's diffusivity. This is just for simplicity. You can choose to keep writing this term every time. But this is your diffusivity equation, which we use in well testing pressure transient analysis. But what we want to do is to solve this more complicated one. For 1D only, we ignore these terms and we solve it numerically. So we're going to use those finite differences I introduced previously. I already showed you these slides when we were in module 1, that solving this problem is similar to breaking down your simulation domain into grid blocks like this, and this is 1D. And each of the grid block is basically a tank model. It's like a tank, a well-mixed tank, meaning the properties within each tank is homogeneous. The properties within each grid block is homogeneous, right? And if you want to increase the accuracy in the solution, well, increase the number of grid blocks or the number of tanks. That makes the system more accurate. So back to the problem we're trying to solve. Each cell has porosity and permeability, right? So that's cell 1, cell 2, cell 3. But the pressures are the interface. Good. Initial conditions, because remember, you need initial conditions and boundary conditions along with the partial differential equations before you can solve the system. That's the same case whether it's analytical solution or numerical solution. So here, at time 0, meaning at initial conditions, pressure everywhere in all of the grid block is Pi. So that will be specified. On the left face, I already mentioned, is a no-flow boundary. We are assuming it's liquid. The word we use is slightly compressible liquid. So it has a constant compressibility value, which is small. At T equals 0, pressure at the right face is lowered to PW. So the pressure on this face is set to a constant value, PWF. I already discussed that before. And the question is, what will be the pressure distribution throughout the domain after 10 days, which is equivalent to 240 hours of production? And the equation we're going to solve is right here. For now, let's assume these values are constant, right? Like in the diffusivity equation. So we are basically solving the diffusivity equation numerically. But you will later see that even if these values are changing, your reservoir simulator can account for that using the same differences we are discussing in this course. So that's your left-hand side. This is your right-hand side. Second order derivative with respect to x, first order derivative with respect to time. This is a conversion factor because your permeability is in millidarcy, your viscosity is in centipoise, pressure is in psi. These are not in a consistent unit like the SI unit system. Time is in hours. That's why you need this value as a conversion factor. Now, consider point 2 in the cell, in the domain, simulation domain we had looked at before. So this was P1, this is P2. So considering P2, we want to use finite difference at a time step of, say, delta t. So the equation we're solving, on the left-hand side, we had this previously, right? Now replace this with the central difference we created, we derived for second order. So second order central difference which we derived is precisely this, right? X plus 1, which is 3, because x is at P2, right? We're at point P2. So this is x, point P2. This is x plus delta x, which will be point P3, right? And x minus delta x will be point P1. So that's the equation. F of x plus delta x minus 2f of x plus f of x minus delta x divided by delta x squared. So we've just substituted the second order central difference for the 2p dx squared. Same as in the previous equation. This is the right hand side, and this we use finite difference. And which one are we using here? This is t minus delta t. Is this forward difference? Is it backward? Is it central difference? First off, you're dividing by delta t, so you already know it isn't central difference, right? Because in central difference, you will divide by delta t. Sorry, you will divide by 2 delta t. So it's either forward or backward. But this is t minus delta t, so this is backward. This is at x. This is at x minus delta x. But here we're looking at time, right? So we are in the same point in space. It's 0.2, but this is at t. This is at the current time step. This is at the previous time step. And that's why here we don't show anything, but here we show t minus delta t. Important to note this as temporal derivatives. When we use the word temporal, we mean time. So these are temporal derivatives. These are spatial derivatives. So we use those words in numerical discretization. And this is your backward difference, first order backward difference. And then we'll later move on to evaluate these. And I'm going to stop here, then continue from here in the next video.